Okay, now we want to look at the next part of our lecture. That's going to be looking at what we call wave interference, as well as wave beating phenomena. We'll look at something called standing waves, and then finally we'll look at something called the Doppler effect. So what is this idea of wave interference? Well, it turns out there's two different kinds. There's what we call constructive interference and destructive interference. And let's look at the constructive kind of interference first. And so we can see it says when two waves combine, so imagine that there's two loudspeakers over here and your ear is in the middle somewhere, and you've got a sound wave coming from one loudspeaker and a sound wave coming from the other loudspeaker, and they both arrive at your ear at the same time. What is it that you're going to hear? Well, you're going to hear a combination or an addition of those two waves added together. Now, it turns out that depending on the conditions, the waves can add together either constructively or destructively. So that's what we want to understand. What does it mean for constructive interference to occur or destructive interference to occur? And that word interference comes from the idea that the two waves, as they add together, they're interfering with one another. So it turns out that if the waves are in sync, and the fancy way to say that is, mathematically you would say they're in phase, but we can think of that as them being in sync. What does that mean? Let me be clear about what I mean when I say a wave is in sync. So I've got a wave here and a second wave, and they're going to be added together. This wave starts at the same time that wave starts. They both rise together. So the time it takes to get to the maximum is the same for each. And then they start to turn around and go the other way. They both are zero at the same time. So everywhere, these waves are copies of each other. They're identical to one another. And when they add together, they reinforce one another. And this is what we mean by constructive interference. So let's just look at a couple of points. So we're going to call the horizontal line in the middle, we'll call that 0. And so when they both start at the same time, they both have 0 amplitude. And so what do you get when you add 0 plus 0? You get 0. So the combined wave at the start is still 0. But let's say you go a little bit to the maximum. Here I've got this maximum plus that maximum. That's going to be bigger than either of these individually. And so you can see when you add them together and you get to the time when they're both at the maximum height, you get effectively a doubling of the height because the two waves are adding together and reinforcing one another. Now, the amplitude is how big the vibrations of the wave are. If it were a sound wave, it would be effectively related to how loud it is. If it were a light wave, it would be effectively related to how bright it is. It's related to the intensity of the wave. Now, if you have these two waves adding together, everywhere they reinforce one another. You can see that when this guy crosses the 0 again, it's 0 there, it's 0 there. It's 0 in the middle here too, because 0 plus 0 is still 0. Down here it's negative, here it's negative, but you add them together, you get an even bigger negative. So having two waves add together, if they're in sync with one another, they're going to reinforce to make a bigger amplitude wave. And that's called constructive interference. Now, what if they weren't perfectly in sync like these two guys? What if this guy was moved over just a little bit, so that was 0 here, this guy was maybe up a little bit higher? You would still get constructive reinforcement, you'd get constructive interference, but it wouldn't be as big as if they were perfectly in sync. Now, we know that the kind of waves that I'm drawing here are what we call transverse waves. Remember, the thing making this kind of wave would be shaking up and down like this, and the wave is traveling at a right angle. That's how we know it's a transverse wave. And so this is just another way of showing the superposition. And by the way, that word superposition, that's just a fancy math word. It means just add them together. The superposition of two waves means the addition of two waves. So I've got these two waves, they're in sync. They both start at the same time. They're reaching their maximums at the same time. They're in sync with one another, or fancy words, we would say they're in phase with one another. They're in phase with one another, so they add together constructively, and they make a bigger intensity wave, a higher amplitude wave. Now, the same thing can, of course, happen with longitudinal waves, like sound waves. Now, remember, in a longitudinal wave, the vibrations producing the wave are vibrating along the motion of the wave. So the wave's going to the right. The thing vibrating to make the wave would be vibrating left to right to be vibrating parallel to the motion. And so you can see where the air molecules have been bunched up here. That's a condensation or a condensing region. And out here where it's spread out, we call that a rarefaction. And if I take two identical waves, you can see this guy's more dense here. We're in that condensation here. At the same time, this guy's at a condensation. And what happens when they add them together? You get an even more intense condensation. So that corresponds to a bigger amplitude of the wave. In this case, it might be, for example, a sound wave. But really, any kind of longitudinal wave can experience this kind of interference. Now, the other kind of interference is what we call destructive interference. This is when two waves combine so that the resulting effect can be for the resulting combination to have the two waves cancel one another. And so this happens when they're out of sync with one another. So here you can see they both start out at 0, but this one is going up when this one is going down. Now, of course, if we add 0 plus 0, we get 0 over here. But here, I'm at the maximum when the other guy is at the minimum. And so I have a positive value and a negative value, and they are going to add together to give you 0. And everywhere on the wave, this one's a little bit higher. At the same time, it's a little bit negative. It's the same amount high to negative, so you get a complete cancellation of the wave. You could actually have two sound waves beamed to your ear, but if they're perfectly out of sync like that, when they strike your eardrum, you won't hear a sound because the two waves will be completely canceled out with one another. And so in the previous example, they both started at the same time. They were both going up and down at the same time, and we said that was in sync or in phase. Here, when this one's going up, this one's going down. When this one's going down, the other one is going up. So they're completely out of sync with one another. We call that being out of phase. And when they're completely out of phase, you get a complete cancellation. Now again, if they were a little bit out of phase, but in a destructive way, you might get some amount of wave over here, but what you would get with destructive interference is that your sum is always going to be smaller than one of your individual waves. With constructive interference, you get something that's bigger than any of the individual waves, all the way up to the maximum possible value, like we talked about in the previous slides. So this is just another picture showing the same thing. We have two waves. As this one's going up, the other one's going down, so we know that they're out of sync with one another. They're out of phase. And this last thing here is just showing the sums. We've got the wave that's up and the wave that's going down, and they're mirror images of one another, really. And so when the waves are mirror images of one another like this, they add together and they cancel, and you're just left with 0. And again, so here we have identical transverse waves that are out of phase or out of sync, and you get destructive interference from that, the cancellation. We can see the same sort of thing with a longitudinal wave. So here we have a rarefaction where the other wave has got a condensation. Here we have a condensation where the other wave has a rarefaction. And so if they're completely out of phase with one another, you get complete cancellation. So there's no bunching up anywhere. There's no condensations or rarefactions. It's just still air in essence. Here's an image of your book. Now, if you want to make two loudspeakers be out of phase, you can reverse the wires to them. Basically, from your stereo to your loudspeaker, there can be two wires. Usually it's like a red wire and a black wire, and one's positive and the other's negative. and you plug them in the way they're supposed to be. So you plug the positive from the stereo into the positive of the speaker and the negative to the negative, and that's the way you normally do it. But let's say for this speaker you've got it hooked up correctly. The other speaker you've reversed the negative to the positive. That means that this speaker is going to be pushing when that one is pulling, and these two guys will be out of phase. And you'll get cancellation if you face them one another, so the sound will be very, very low because of destructive interference. And if you push them just the right distance to each other, and one of the right distances would be right next to one another, you'll get complete constructive interference. In other words, you won't hear any sound at all. Now, this next topic is related to what we were just talking about, but it's different, and that can be a little bit confusing. So this is the topic of beats, and it uses constructive and destructive interference, but it's in a different way. So, we're talking about a completely new topic here. Just be aware of that. Now, this is one of those times when I think it might be easier to just describe how it works before I actually tell you what it is. And then once I describe how it works, I'll be able to explain what it is. So the idea here is I've got two tuning forks, but they don't have identical frequencies. They have slightly different frequencies. If the frequency difference is too big, if they're way off from one another, you won't get this. But if they're close enough together, you can get this phenomenon that we call beating. Now, let's look at this first tuning fork. In the time it takes the sound waves to go from here to here, so from the tuning fork to over here, it's had 1, 2, 3, 4, 5, 6 condensations and rarefactions. And so that would be, let's say it takes 1 second to get to here, that would mean the frequency was 6 beats per second, or 6 hertz. Now here, you can see that this guy is got 1, 2, 3, 4, 5, 6, 7, 8 condensations. And so 6 to 8 is pretty close together. And what you can see is the difference between 6 and 8 is 2. Right? So hold that idea in mind. The difference between the frequencies is 2. Now let's look at these patterns here. So we've got a condensation for the guy here when the other guy has a rarefaction. And then this guy's condensation is when he has a rarefaction. So guess what? These guys are effectively out of phase, so they're not going to be reinforcing one another. But because in the same time interval, this one has 6 rarefactions and condensations when this one has 8, the timing is going to be different. But eventually what you can see is right here, the condensation of this one and the condensation of that one occur at the same time. So guess what? The sound is going to get really loud when the two match. And then they're not matching together, but eventually they come back together and they're matching again. And so the sound is going to get really loud. And so what you'll hear when you strike these two tuning forks, you're going to hear the sounds of the two tuning forks, but there's going to be what they call a beat frequency, where it gets really, really loud, and then it gets softer, and then it gets really, really loud again. That's because the condensations are lining up to give you a maximum amplitude. Now, remember we said that the difference between the frequency was 2? Well, guess what? You get 2 beats, 2 places where the constructive interference lines up. And so that's characteristic of the beat frequency. It's the difference in the frequency of the 2 sound sources. And I'm going to try to get a video up for you guys that will actually demonstrate what this sounds like so that you can, kind of get a better feeling for it. But hopefully the explanation that I've given here will make sense to you so that you can understand how, when you have 2 sound sources together, they can have interference that's constructive and destructive in such a way that when they line up time-wise, that you get reinforcement, and that creates a loudness and a softness from that kind of combination. The next thing that we want to talk about is what are called standing waves. Now, In a standing wave, you have, for example, a string that's tied to a wall or somehow fixed to the wall, and you pull the string out and then you shake it up and down. So we're going to make transverse waves going this way. And of course, you can have standing waves with longitudinal waves, but it's easier to see with the transverse ones. So that's usually the way it's described. So this girl here is sending a wave by shaking this up and down, and so the wave travels and then it hits the wall. Now, what happens when it reflects is that it reflects inverted, and so it's going to reflect with an so you can see that this one is coming down, the reflection is going to be like that. And if those were the only two waves, you would expect them maybe to cancel each other out. But what's happening is this girl is continuing to shake up and down and send new waves across, and then you're going to have, each time they hit the wall, they're going to reflect, invert, and go back the other direction. And if the frequency of the shaking up and down is just right, you get what's called a standing wave. Now, a standing wave is hard to describe with a static picture like this. It's really, really difficult to explain what's going on. So I'm going to put a video up in the supplemental video section that has a really nice animation to describe how this actually happens to help you understand it. But there are a couple of points about standing waves that are worth mentioning here. The first is that every standing point will have points that are called nodes. And you can see the node is where it's at 0. And the standing wave here is going to be traveling like this. At a different time, the standing wave might be doing like that, or even down below and then going up. These are like basically snapshots of all the waves going forward and all the waves going backwards added together, superimposed on one another. So you could see each one of these lines represents a particular moment of time when the wave looked a particular way, as the forward moving wave and the reflected wave were passing through one another and interfering each other. Now, the envelope of the wave, however, is static. So the way I try to describe it is like this. Imagine that you are a bug on the string. If you were right there, that string is going to go this high back and forth, constantly up and down, but only this high and no higher. If the bug were to crawl to the place where the maximum vibration is, the bug would go up and down, and it would swing much higher. And so it's hard to show this with a static picture, but that's what's going on. Now, the weird thing is, if the bug were to crawl right to the center where this is drawing what's called a node, then the bug is not going to go up and down at all. It can be, if the bug is here, it's going to have to hold on for dear life to keep from being shook off. But if the bug is at the node, there's no vibration up and down at all, so he can happily take a nap there or whatever. Now, normally we think of waves as traveling, and indeed, there is a forward traveling wave towards the wall. It hits the wall, and there's a reflected wave, which is traveling in the other direction. But we don't see that traveling in a standing wave because the two waves add together and create these sort of, not necessarily static shape, but the same shape over and over again in the same spot. So the bug again here, wherever the bug is, it's always going to execute the same motion up and down. And that's why we call it a standing wave, because it doesn't seem to have that left and right motion. We know that really there's the rightward motion of the forward wave, there's the leftward motion of the reflected wave adding together, but the standing wave itself doesn't seem to move left or right at all. It just seems to be moving up and down, and every place is moving up and down a different height. That's why we call it a standing wave, because it doesn't seem to be moving left or right, it just seems to be stationary. Now, the last thing that we want to talk about in this part of the lecture is the Doppler effect. The Doppler effect is all about what happens to sound when the thing making the sound is moving. It could also be when the thing receiving the sound, whether it be a microphone or your ear. Basically, if the thing making the sound is moving, or if the thing receiving the sound is moving, or if they're both moving, you can have the Doppler effect come into play. But it's easiest to understand with the idea of the source being the one that's moving. So we'll take that as an example, but just be aware that the source could be stationary and you could be running towards the sound or away from the sound and get the same kind of effect. So what is it? So let's consider a bug that's resting on the surface of a water, and the bug is wiggling back and forth, and that's sending out waves outward. And we know that those waves, those water waves, from the top view are going to look like concentric rings traveling outward. And each of these rings represents a crest of the wave. Now, if you were over here, you could feel each crest of the wave passing you, and you could figure out, 6 crests passed me in 1 second. So that's a 6 hertz wave or whatever it is. So that's how you tell what the frequency is. You're detecting how many crests pass you every second. Remember, that's what the frequency of a wave is. It's the number of complete cycles that happen every second. Now, if you're here and your ear is at point B, and the bug, as it's making these waves, starts swimming towards you, what's going to happen is the waves are going to bunch up on the side towards you, and they're going to spread out on the side away from you. And we can see this in this picture on the right here. So what you see is 4 different positions, 1, 2, 3, 4. And those correspond to the 4 different waves, wave 1, wave 2, wave 3, and wave 4. And so wave 1 was the first wave crest that's sent out, and you can see that 1 is the center of this wave. Now, over on the left here, this bug is wriggling back and forth, so it sends out the first wave, which is actually the one on the outside, and then it sends out the next wave, and then it sends out the next wave. And so the waves that are closer to the bug are the more recent ones that were sent out. The original wave is the one that's the farthest out, and that's true here. Wave 1 is the biggest circle, and it's centered here. Now, if the bug were sitting still, it would make the picture that looks exactly like over here. But what happens is from the time that the first pulse is sent out to the time that the second pulse is sent out, the bug has moved from position 1 to position 2. It's swimming towards B. And so the second wave is centered at position 2, and that's that wave. And of course, if the bug were to stop there and stop pulsing, you just have those 2 pulses. But the bug is continuing to make waves and continuing to move over here. So the third pulse is made when the bug is at position 3. You can see that wave 3 is centered at position 3, and so on. Now, what that has the effect of is the waves bunch up on this side and they spread out on the other side. So you're moving towards B, they bunch up towards B. So they bunch up in the way that the thing is moving, and they spread out opposite to the direction that the bug is moving. Now, what's important to note is that in both of these pictures, the bug is actually making the same frequency of wave. The frequency is not different. However, if you are counting the number of crests that pass you at point B, can you see that because the crests are bunched up closer together, it would seem like there were more crests per second than over here? And so bop, 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 bop. It seems like the frequency's higher, and in fact, you would feel the frequency being higher because of this motion. And that's what the Doppler effect is. It's the apparent change in the frequency of a wave due to the motion of the source of that wave, or the motion of the observer. Again, if the guy was sitting still and the ear, the thing with, or the microphone or whatever, was moving towards it, you would still get faster, you would encounter these pulses more quickly, and the frequency would seem to be higher. That's the Doppler effect in a nutshell. Now, what if your ear were over here at point A? The bug's still swimming towards B, but over here, the waves are spread out more. And so the frequency that you would detect, the number of crests per second, would be lower. And so if the thing is moving away from you, the frequency of the wave it emits seems to be lower. If it's moving towards you, the frequency of the waves that are emitted seem higher. That is the Doppler effect. Now, here's a practical, everyday application of the Doppler effect that most people have experienced in their life. If you've ever been by the side of the road when a car was coming towards you, if you listened to the sound of the pitch of the engine, and pitch is related to frequency, so what you're hearing in terms of the pitch is related to the frequency of the sound being made by the engine, it's going to seem louder because the car is getting closer to you, but that's different from the pitch, which is the highness or the lowness of the sound. If you are playing a piano and you play one of the higher notes, it sounds higher because the strings are vibrating at a higher frequency. So the pitch is higher. So don't think about it being louder or softer, but just focus on the pitch of the sound. The sound is either a higher frequency or a lower frequency. When the truck is moving towards you, the sound waves bunch up and the pitch that you hear is higher. And then the truck goes past you, the waves are spreading out, and the sound you hear is lower. And so you get a change in the quality of the sound, the pitch of the sound, based on whether the truck is moving towards you or away from you. That is the Doppler effect. And again, I'll try to put another video in the supplemental videos that will better illustrate this and give you some actual practical examples.